So I request the resource person, esteemed Professor Rajni Kant, for his dissemination and invite him on the dais to interact with the students on your topic. Thank you, sir. Welcome.
Thank you very much, Professor Rahul. He has spoken too much about me. Well, he rightly said that I am, one of the hosts for this science festival, and I decided that I should also speak to the audience who have come from the colleges, the universities, and our young friends from the university itself. I have chosen a very general topic for deliberations, that is the past, present, and future of radiation technology and its applications. Ever since we are born, we have known that sun is the only source of light for us, natural source of light for us. And whenever it is too chilly, the weather, we go to the sun, get the dew warmth from its radiation, and feel safe and happy and protected. And when it is too hot, we go to the air conditioner environment and enjoy our life. I have today decided to speak on the past, present, and future of Am I audible? Okay. The slide doesn't move. On it. Slide. इसको इनको always whenever we have to organize some functions, so these small little technical glitches are very important. Okay. Can you move on to the first slide, please? Yes. अगर ये ठीक हो जाता है मुझे बता दीजिए. वो pointer भी चला गया. Anyway, doesn't matter. I will have to direct my slides with my finger. So in physics, the radiation is the emission or transmission of energy in the form of waves or particles through space or through any material medium we have. I am talking to you, you are listening to me. There are, the waves which are, passing through the material medium present in this auditorium. We have heard about radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X radiation, and gamma radiations. These are some of the very common words which we are aware of, which we know they are, a little bit of application potential also. People who are using microwave ovens in their houses, they also know, that how the heat actually passes through the medium, through the product which they want to heat up. Radio waves, everybody is listening to AM and FM, that is amplitude modulation and frequency modulated frequencies. Visible light, we all are aware of. Ultraviolet radiation is, a bit harsh in the sense that we are not sensitive to ultraviolet radiation. Then we have X-rays, again high energy radiations, and gamma radiation, of course. Yes. Gamma radiation, of course, is the highest frequency radiation. Radiations are classified into various categories. One is the particle radiation. This is called alpha radiation, beta radiation, proton radiation, and neutron radiation. Then acoustics, the sound, ultrasound, sound, and seismic waves, which predicts the onset of, the earthquakes. Then we have gravitational radiations, in which the ripples are found in the curvature of the space-time continuum. Radiations are of two types. One is ionizing radiation and another is non-ionizing radiation. Except these two, there is no other relevance of the radiation. Either it ionizes or it does not ionize. The word ionize refers to the breaking of one or more electrons away from an atom. It breaks one or more electrons away from an atom, and this is an action that requires relatively high energies that the waves supply, because the energy is flown with the wave itself. And non-ionizing, the word refers to lower energies which cannot ionize atoms but do have the potential to disrupt the interatomic bonds which form molecules. So therefore, they break down the molecules rather than breaking down the atoms. For example, the simplest example of non-ionizing radiation is the sunburn which are caused by long wavelength solar ultraviolet radiations, for which we have a lot of sunscreens available in the market, SPS 30, SPS 40, and so on and so forth. Ionizing radiation carries more than 10 electron volt energy, which is enough to ionize atoms and molecules and break the chemical bonds which makes the molecules. And a common source of ionizing radiation is the radioactive material that has the potential to emit alpha, beta, or gamma radiations. If you put a piece of paper in front of the alpha radiation, even the paper has the potential to stop it. It will not allow it to pass through the paper. Whereas beta radiation can, even be stopped with the aluminium metal, and gamma radiation can be completely stopped by using the lead as the shield because of the high atomic number it carries. I will be speaking about only the spectrum, the electromagnetic spectrum, because this is the Makkah and Medina for defining radiations of various kinds on the basis of their frequencies and amplitudes. If you look at this spectrum, this is our wavelength and this is frequency. Frequency and wavelength are reciprocally related to each other, inversely proportional to each other. Greater the frequency, lesser the wavelength. Greater the wavelength, lesser the frequency. We have, categorized, not we means me, I mean, the work done by earlier scientists, that the electromagnetic radiation spectrum has been divided into various units. It starts from 1000 meter range, that is AM, radio range, amplitude modulation. But corresponding frequency is very less, it's 10 raised per 6 hertz. And when we go beyond the radio and television signals, then we enter into the zone which is called microwave zone. Here, the wavelength is 10 centimeter to 1000 micrometers. But if you look at this range, the radio and television, it is further divided into 4 units. One is called the FM, where the frequency can be tuned to have access to the broadcasting station. These are of 3 types. That is very high frequency radiations, high frequency radiations, and ultra high frequency radiations, for which the frequency can go up to maximum 1000. You know what is the unit of frequency? MHz stands for megahertz. Megahertz. Then above the microwaves we have the infrared region, where thermal IR and far IR, this is a terminology which is known to the chemists, therefore I avoid it. Then we at 1 micrometer to 1000 nanometer, we fall into the region, we call it as the visible region, and this forms the spectrum for the visible light, and the corresponding frequency is 10 raised power 15 megahertz. Beyond, if we tune further the spectrum and take the frequency to 10 raised power 16, then we go into the ultraviolet region, and beyond that, that is 10 raised power 17 to 10 raised power 18, we have the range of frequency in which the most important radiation, that is X-rays, lies into. And beyond this, that is 10 raised power 19, is the gamma rays. And look at the corresponding wavelength, 0.1 angstroms. Now, 10 raised power 19 is the limit. Beyond this, we have never been able to make any system workable in laboratory conditions or, in the environment. The simple reason is that if I go from 0.1 angstrom wavelength to 0 angstrom wavelength, then frequency will become infinite. And there is no physical system on this planet for which the frequency can go infinite, because if it happens so, we won't be able to really have any equipment to measure the frequency of such system. So therefore nature has put a limit to the frequency and to the wavelength for the electromagnetic spectrum. The waves of longer wavelengths than ultraviolet in visible light, infrared and microwave frequencies cannot break the bonds. These waves cannot break the bonds, but they can cause vibrations in the bonds which are sensed as heat touching the human body or any biological system. Radio wavelengths and down below this wavelength are not regarded as harmful to the biological systems. That is why we always, we have seen our elders keeping the radio very close to the pillows they used to sleep on, and would listen to some interesting programs. So radio waves are not at all harmful to the biological systems and not ionizing itself. Ionizing radiations has many practical uses in medicine, research and construction materials, but it do carry a health hazard if used improperly. I will let you know all the positives, pros and cons of these radiations which are ionizing in nature. The exposure to radiation causes damage to living tissues, and high doses result in skin burns, hair loss, internal organ failure and even death, while any dose may result in an increased chance of inflicting cancer or creating genetic disorder in humans. This is a better version of the electromagnetic spectrum. If you see here, this is that was the vertical image, this is the horizontal image. So our span for the wavelength is 10 raised power 6 to 10 raised power minus. How much it is? Minus 16. Okay. and the corresponding frequency is 10 raised power 2 to 10 raised power 24 megahertz. This is the visible spectrum where you all know it. It is known as Vibgyor, 7 colors. If you further amplify, zoom this image, you will find all the 7 colors present in it. Now I would like to take you to the concept of only one radiation, that is X-rays, because the radiation physics itself is a course in itself. It is not possible for me to, speak on all aspects of radiations in 30-40 minutes. So therefore, I have focused myself on X-rays because this is an area in which I have worked for over 38 years, and I thought that I must tell my people over here that how this radiation can be used and abused also, and what are the areas of applications where this radiation can be employed for making the human life better. This is the picture of the laboratory taken in 1895. This is the laboratory of William Röntgen. He is the man who is working in this laboratory, and you look at the kind of scientific infrastructure they have. When he was, while carrying out a cathode ray tube experiment, he found a huge spark in the room, kind of a flash, and about which he was, literally speaking, he was shocked to know that what had happened. And next day he wanted to repeat the same experiment. He found that the flash of light is, still there. He discussed this phenomena with many of the contemporaries present in Germany. So he realized that this is some kind of radiation about which he has no knowledge that what is it. So therefore, when he submitted his work for publication in a research journal, he called this radiation as X radiation. X means cross. Cross means that nothing is known about this radiation. So since then, we all on this planet know this radiation as X radiation, because that time no property of this radiation was known to the mankind. So therefore, later on, when all its properties and its applications were made available to the world, people thought that now we should replace this word cross. That cross you find here on all the chairs also. Okay? So people thought that in order to give or be reverent to the scientists who discovered it, so they continued with the symbol X, and this is how X-rays came into existence. This is the first X-ray photograph which has been taken on 1st January 1896. This is the right hand image of his fiancée, who also used to work, Röntgen's fiancée, who also used to work in the same laboratory. And this broader, portion here indicates the engagement ring she was wearing, and because they were not married at that time, they were only engaged. And hence this became as the first ever X-ray photograph recorded on a human body. So, going to X-rays, X radiation, it is composed of rays which are nothing but a form of electromagnetic radiation, and its wavelength range is 0.01 to 10 nanometers, and frequency is 10 raised power 16 to 10 raised power 19 hertz, and this is the energy range at which these X-rays can be generated. And these are also known as Röntgen radiation because it was discovered by Röntgen. And for this useful discovery, the first ever Nobel Prize in Physics was awarded to him in the year 1901. And since then, in the last 121 years, You will be happy to know that 36 Nobel Prizes have been won by the people who work in the field of X-ray crystallography. That itself shows the commendable contribution this field of science has made to the lives of humans, and also to those who are non-living, that is the materials. I will touch upon both the aspects of this radiation. This is anyway now the question arises that what are the sources for the production of X-rays? If you look at the periodic table, nature has given us a very limited number of elements, 118 elements, and all have been arranged in the order of their atomic number. And if you ask me that how many materials can be used for the production of X-rays, I would say maximum 4 or 5. I will tell you the reason that why nature has been so choosy about giving us the materials for the production of X-rays. Any material you pick up, here for example I am showing you the wavelength versus intensity graph for molybdenum element. The molybdenum, when you accelerate the beam of energy and allow it to fall on the target material, and if your applied potential is 10 kV, the wavelength is somewhere near 1.2 or 1.3 angstroms, and the peak would go up and then immediately it will fall down. You slightly increase the potential, take it to 20, the peak further goes up and then it goes down. And a stage comes when you increase the potential from 25 to 40 kV, you find a characteristic peak over here, 1 and 2, these two peaks over here, and then it takes the form of the fall of the wave. So these three fall off regions are known as the continuous radiation spectrum, and these two peaks which are quite characteristics of their material are known as characteristic X-rays. These two peaks are actually the ones which decides that what kind of material should be useful for the production of X-rays. This is another better view of that two peaks. One is K beta, the smaller one, and the bigger one is K alpha. These two peaks, if you go for hyperfine or high resolution breakup of these two peaks, you find that this is not only K alpha but this is a doublet. K alpha 1 and K alpha 2, two components for this and two components for beta, K beta 1 and K beta 2. And if we calculate the intensity of K alpha radiation, that is the intensity of K alpha 1 peak and intensity of K alpha 2 peak, the ratio of this K alpha 1 and K alpha 2, the intensity ratio should be equal to 2. This became the defining parameter for the scientists to know that any material, any element picked up from the periodic table, okay, if its wavelength versus intensity graph gives us a peak whose ratio comes out to be equal to 2, would be ideal for the production of X-rays, whereas the intensity of the K beta 1 and K beta 2 is of course going to be unity, because the peak width here is not much here, the peak length is too much and width is also divided into two components. So this is the reason that nature has given us only copper, molybdenum, cobalt, zirconium as the potential sources for the production of X-rays. X-rays are a dangerous phenomena because you cannot detect them, you cannot see them, You cannot sense them, you cannot smell them. They travel in straight line at the speed of light and they penetrate into and through matter they generate charged particles and have the potential to destroy and damage the human tissues. This picture will tell you the application potential of X-rays. That is, I start from here. This is for the airport security. Whenever you fly by air, you put your luggage in X-ray scans, and this is how the person operating on the monitor can know that whether whatever contents you are carrying are okay, worth taking along the flight, or you are carrying something mischievous. Then this has the potential to be used in medical diagnostic techniques like CAT scan and mammography. And here, this is the most potential area of application, that is called the X-ray crystallography. So X-ray crystallography and medical applications of the X-radiation I will dwell upon in my next slides. Very often you must have seen that whenever some problem happens in the body, the bone fracture or ligament fracture or some kind of spinal problem, lumbar problem, or any slip that is happening to any muscle or bone, we immediately go for X-ray examination, and this is a conventional hospital radiology room where the X-rays are usually taken. And you will be, it is important for you to know that the X-rays we use for the examination of humans are soft X-rays. They are not hard X-rays, whereas hard X-rays are used for the analysis of materials. They are soft X-rays. Even then, the exposure time is literally speaking in milliseconds, if not in seconds, because too much of exposure to the human body can cause various problems. So X-rays, therefore, are useful for the detection of pathology of the skeletal system and may also be used for detecting some disease processes in soft tissues. For example, chest X-ray, which can be used to identify the lung diseases such as pneumonia or lung cancer. The abdominal X-ray can detect intestinal infections or obstructions. Kidney stones or cavities can also be diagnosed by using X-rays. CAT, this is whenever you go to the hospital, you find CAT scanning rooms, CAT scanning rooms. The CAT stands for computer axial tomographic technique, in which it is a one step above the conventional X-ray, which can detect the fracture or dislocation in a human body. But because the resolution of conventional X-ray is not that good, so therefore a higher and a better technique was developed, that is known as CAT scanning, CT scan. This is how the skeletal structure of a human body looks like, and here if you see from head to toe, one can very easily look into the minute details of where the problems are happening. This is a conventional view of the machine which can be used for obtaining full body CAT scan. This technique is also useful for sometimes people, you must have heard that they are suffering from tennis elbow problem. Tennis elbow is quite common in players. Okay, this is a problem where bone actually is not the issue. It is the muscle that is engulfing the bone is problematic. So therefore, X-rays since cannot take care of conventional X-rays cannot take pictures of the muscle, the fiber around the bone. So therefore, high resolution X-rays can be obtained, which takes a three-dimensional view of the problems, and even they are capable of finding the spacing, whether the fluid is able to pass through the femur and the down below bone. So therefore, this computer-aided tomography techniques can be used for the diagnosis of bones and human body as a whole. Now, if you fluoroscopy is another technique which is again a technique useful for treating the people who suffer from the heart disease, and especially the people whose pulse is obstructive and cannot really breathe normally. So any kind of disharmony in there are arrhythmic conditions which are created to the heart due to certain reasons, lack of oxygen or the compression of the lungs. So a stent is always put in such people so that with the help of battery a continuous pacing is set and heart is able to make the blood flow from the upper ventricle to lower ventricle. When that pellet, that what do you call it as क्या बोलते हैं अभी मैंने यूज किया ना pacemaker. When the pacemaker is implanted in the fiber, it carries two leads. One lead is attached to the upper ventricle, another lead is attached to the lower ventricle of the heart, and it takes around 2 to 3 weeks for the pacemaker to get embedded in the fiber. So therefore, after the pacemaker is implanted, it is essential for the person not to make too much of body motion or walk or jump around or dance, because the position of the pacemaker once disturbed can lead to sudden death of the person also. So therefore this technique fluoroscopy is used as a tool for recording the three-dimensional movement or dynamics of the heart and the pacemaker, and after the pacemaker is planted, every third or fourth day the patient is called to the hospital for carrying out the fluoroscopic investigations. The third and the most important part of treating people suffering from cancer is the radiotherapy. Radiotherapy is the first part of the treatment, followed by chemotherapy, that is the second and the last part of the treatment. Radiation therapy is age-old technology which is being used for treating the people suffering from any kind of cancer. What happens is that once you have a tumor in the body and it is extracted by doing the surgery, thereafter the area is mapped and a high dose of radiation is allowed to fall on the cancerous region, so that the adjoining area where healthy tissues you have, they should not get infected with the cancerous cells. So therefore we try to kill those cancerous cells. In this process what happens that while killing the cancerous cells, the healthy cells are also killed, and which actually creates a lot of problems for the patient. So now the dose is, these days is monitored in such a way that after effects of the radiation therapy are lessened to the large possible extent, and the person should remain comfortable. The last 10 years or so, another technique better than CAT scan, that is called MRI, and thereafter MRI we have a mammography technique. That is what's happening. Mammography technique, which is essentially used for the breast examination of females. If you look at the world statistics today, 80 to 85% of the breast cancers are generally found in females. In America, it is essential for any teenager girl beyond 18 years and above to undergo once in a year mammographic examination, so as to avoid the occurrence of breast cancer in females. This is the most advanced technique now, which is available in almost all hospitals. And this is the setup which is used for the evaluation of the breast tissues. If you look at this picture, this is the conventional X-ray picture of a breast where you see a lot of haziness around. You cannot really see through anything, foreign existing in this breast. Whereas a slightly better, higher resolution image of the same breast will give you, some better insights about the internal mass of the human breast. Here, if you further increase the resolution and reach up to this level where you are able to see the point where malignancy is erupting, you can, map that area, and before it gets worsened, you can immediately go for extraction and, the procedure, incision can be given, and, this tissue can be taken out, and the person can be saved from the consequences of the treatments like chemotherapy and radiotherapy. So mammography is in fact the most advisable technique for the young girls. It is important that we get them covered under this technique, and once in a year at least we get the breast examination done so as to avoid the incidence of cancer in the females. These are the, some of the health risks of radiation, which I have already spoken about. Now I tell you about the future applications of X-ray technology in medical science. Apart from what I have spoken, recently Siemens is likely to launch a new robotic X-ray room technology, which is designed to be an all-in-one machine capable of undertaking various imaging applications. You don't really have to go for conventional X-ray, CT scan, MRI, mammography, radiography. This technique is going to be, one fits in all kind of a situation where from anything to anything, from anywhere to anywhere in the human body, anything happening, and it will give you the three-dimensional view of the problem. So therefore, this way, the exposure to the human body of X-rays is going to be lessened to a very large extent. Because once you go for conventional X-ray examination, and if the doctor is not happy with the photograph or the image, he would say, आप CT scan करवा के आइए. अगर CT scan भी दिखाया तो उसको अगर clarity नहीं है, वो कहेगा इसकी MRI करवा के दिखाइए. How many times the human body will get exposed to X-rays? So therefore, this Siemens is going to come out with a, very mechanized kind of a setup where all is possible in one go. So you don't have to really undergo periodic exposures to X-rays. Other application techniques of X-rays are to the science of materials. Quite almost every day we watch television, and you must have seen that few advertisements like Ultra Tech Cement, sadiyon ke liye, TMT Saria, all these advertisements, you see that the material which we use for the construction of houses, they do carry, such slogans that our cement or our steel bars are the best, and they can give you a house which can last for 100 years or 150 years and so on and so forth. So it means that it has to do something with the quality of the material. So for qualitative analysis of the materials, X-rays are highly useful and extensively used for maintaining the chemical composition of the materials. This can be used for phase identification, crystallographic analysis, texture analysis, and micro diffraction. I am not going to give you any research presentation to bore you people. So therefore, I will immediately take you to the past and present of the X-rays, and in the last I will tell you about the future of X-rays. To do X-ray analysis, you need to have a material. A material is something which we call it as a solid material or a liquid material, depending upon which class of matter you are going to deal with. A solid is, by definition, if you ask, it is something which has some shape and occupies some space, is known as a solid. And once you have a given solid, you carry out its X-ray analysis, and the X-ray analysis gives you the internal exposition of this material, because a solid is nothing but it is composed of n number of planes, three-dimensional planes which are present in the crystal. And you will be surprised to know that a material as small as having dimensions of 0.1 millimeter cube, 0.1 millimeter cube, is likely to have 40 to 50,000 planes present in them. And the job of X-rays is to go down to each plane, diffract the X-rays from that plane, and this is how the diffraction phenomena is recorded in the form of spots on the X-ray film. And when this data is dwelled upon by using various computational and crystallographic analysis, we compute the structure, three-dimensional structure of the materials. So this is the basis for the X-ray crystallography, which is the most essential aspect of material science these days. How this happens? This is a conventional X-ray tube. This is the sample C. X-rays are falling. This is the camera. Diffraction takes place, and by using this simple formula, we can calculate the Bragg angle theta. And if we substitute these values of theta for E corresponding to each reflection in the equation 2d sin theta is equal to n lambda, that is Bragg's equation. If we substitute the value of theta, lambda is the wavelength of the radiation which is known to us, we can calculate d. D is the interplanar spacing. See, by using X-rays, we have the capacity to find out the interplanar spacing for the planes whose number is around 40 to 50,000 present in a crystal of having size 0.1 millimeter cube. So that is the most wonderful property of this wonder radiation, that is X-rays, that it can go deep inside and give us the contents in the form of a photograph. And this is how various X-ray photographic techniques can be employed, and this is how we do the reciprocal mapping of different planes. And this is the setup for putting the crystal on the top of this here, on the tip of this goniometer, and this is how the whole setup looks like. This is called a single crystal X-ray diffractometer. This is a Oxford diffraction machine which is available in our laboratory as a DST sponsored national facility. I obtained it under a mega individual centric research project, and here if you see, this is the goniometer head and the sample is mounted on the top of this. This is the X-ray tube. This is the collimator. Collimated beam of X-rays fall on the sample. This is the charge coupled device CCT camera, which is which operates at minus 40 degrees Celsius. And here, this is the cryo system. This is the liquid nitrogen, which is put on the sample if we have to go beyond 0 degree Celsius calculations. So the diffraction phenomena is recorded, and since X-ray exposure to the human body has to be avoided, so therefore the entire setup is kept in a glass silica enclosure here, and here is the video microscope. From outside we can see the 1000 times bigger image of the 0.1 millimeter cube sample, and we can see whether the the sample is falling in the line of the incident radiation or not. This is the operational view of the single crystal X-ray diffractometer, which is available in our laboratory, and it has given service to us for 16 years, and due to now certain technical snag, it has gone down. But this is really the most advanced kind of a machine, whose estimated cost in the international market is around 400 lakhs. This is how the three-dimensional structure, when obtained by using X-ray diffraction technique, looks like. I will not go into how do we do it, and I will give you only the practical application of X-ray crystallography. X-ray crystallography is now extensively used in defining and making different polymorphic modifications of the materials, especially polymorphic modifications are used in the field of pharmaceutical industry, and also there is another field which has come up because of the wide range applications of X-ray crystallography, is known as crystal engineering. This is a field which is based on the interplay of interactions, intra and intermolecular interactions taking place in the materials of interest, and this is extensively used for the pharmaceutical drug development. Now, this is something which can be done in the laboratory, but what about the materials which we use in the construction industry, that how X-rays are going to be useful? Quite often you have read it in the newspapers and in the TV news also, that while making a building, suddenly the building collapses, or a flyover or a bridge under construction goes down, and the finding would be that poor quality of material was used. By using, the word poor quality means that not that less amount of material has been used, but the reason is that right kind of elemental composition is missing in the material. That is what makes one material inferior to another. So chemical analysis can be done very easily if we allow the material to undergo a simple X-ray scan. In any cement industry, if you see, you will never find a cement industry which does not have an X-ray installation. X-ray machine is available, because when the final product goes for packaging, it has to qualify the X-ray examination, so that to ensure that the elemental composition or the chemical composition remains the same. So is the case in case of the building materials, that is iron bars, steel bars. Quite often you have seen that for a different kinds of iron bars, you find that some kind of droplets, air, gets trapped while the iron is being casted in the form of long bars, and therefore the tendency of that bar to get broken due to the existence of the air cavity is, the chances are more that it breaks down. So therefore, in order to avoid that, that has to undergo again the X-ray examination to see whether there is any kind of impurity in the final product or not. So all these materials, they undergo X-ray examination so as to provide the customer a product which has quality certification. Now, so far as the future application of X-rays to the science of materials is concerned, this is the image of the rover camera which has gone to the Mars for evaluation of the Mars soil, to sense what kind of elements are present over there, whether we have all those elements which are available on the planet for a human life to exist, or was there any signature or biosignature of the human life present on Mars. This is, the camera which has been designed and has, gone into the Mars surface, which clicks the soil data, elemental analysis for the Mars soil. This is, it's bigger configuration. I will not like to go there, but these are some of the future applications of the X-ray technology. And this is a relatively older picture of my students in the X-ray laboratory of physics department. And this is me, with a lot of thanks to the audience. Any questions, please?
Any questions from the audience? Sir, rather, am I allowed to ask a question?
Please do that. Please do that.
It was a very innovative, in very simple languages. You have a language, you have explained the interface between all sciences. You have used mathematics, you have used life sciences, you have used pharmaceuticals, everything has come to this, and it's a very motivating and very good lecture, sir. Sir, I have one query, that these kinds of studies, the energies you are talking about are from materials, X-rays, all these. But is there any study going on to study the human minds, the energy which we emit, negative energy, positive energy? So it is applicable to human beings also, or any studies?
Actually, if you see yesterday when Professor Malhotra was making his presentation, he spoke about neurons, the electrical impulses going on the human mind and the signals transmitting. There is a separate field of science that is called neural networks.
Neural networks.
Neural networks, which is happening world over, but so far there has not been any commendable breakthrough, which is really can make reading the human mind possible.
Kind of X-ray of human minds.
Yes, but I don't think it is something which cannot be achieved. Probably a time or age or stage will come when this will be possible. But by that time, whether we will be on this planet or not, I don't know.
Thank you very much, sir. Now I request Professor Seema Langar, Professor Kamal, Professor Satyapal, Professor Sanjana Kaul, please come on the dais and present a memento, a token of love from the organizers to another organizer who is at the present is playing the role of the resource person.
From the organizer to the organizer.
It was very good, sir.
Thank you.
Because the way you explained it was understandable by small kids also, school-going kids also.
Yes. That was an attempt.
Yes, sir.
That was an attempt. Thank you, ma'am. Thank you so much. ये मैं इधर रख देता हूँ. It should not spoil the pic, na? Thank you. एक चीज का फायदा हो गया, इससे कम से कम पेट का वॉल्यूम नजर नहीं आएगा. Thank you so much indeed. Grateful.
Now you have a